Good day. For those of you who don't know us, we are the instructional staff for ECE 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to introduce the next section, Algorithms and Templates. So in this topic, we're going to introduce the idea of an algorithm, see that the function is the ideal mechanism for implementing algorithms, introduce the idea of an algorithm design technique, and describe how we will be able to generalize our algorithms for arbitrary data types. Now, up until this point, we have focused on programming syntax. We've looked at the basic syntax, functions, condition statements, for loops and while loops, and we described the structured programming theorem. We described console input and output, data types and binary, as well as hexadecimal representations. We looked at arithmetic, comparison, logic, assignment, and bitwise and bit shift operators. We also looked at arrays, addresses, and pointers. Now, the last section covered addresses and pointers, and that is something that's almost new to all of you. So, if you did not understand that thoroughly and still are worried about it, don't worry, this next section does not require you to understand addresses and pointers. However, you will, of course, need to know that for subsequent sections. But for now, you can breathe a sigh of relief, but please do continue to look at addresses, pointers, and try to get a grasp on those concepts. Now, algorithms. We've already seen that a program is a sequence of instructions that has the processor perform a specific task. Easy enough. An algorithm is a sequence of instructions that solves a specific problem. Alright, so it's not related necessarily to a programming language. Instead, it's just a set of instructions. More formally, an algorithm is a description of a process for solving a problem through a sequence of well-defined, precise, and unambiguous instructions. An algorithm has a well-defined set of requirements that must be met to allow the algorithm to successfully find a solution, and the algorithm will, of course, describe the format of that solution. Now, you've already seen a number of algorithms in both elementary and secondary school, even if you didn't call them that. For example, you saw that you can find the quotient and remainder of one integer divided by another by performing long division. You also, using this idea, could determine if one integer m is divisible by another integer n. How? By just seeing if the remainder was 0. You can determine if an integer n is prime. That is, does that particular integer, when divided by every integer between 2 and n minus 1, have a non-zero remainder? That's a little bit more work than just seeing if one integer is divisible by another. Now you have to check all of them. Consequently, you can also determine the prime factorization of an integer n. You can also find the greatest common divisor of two integers, m and n. And using this, you can determine if two integers are relatively prime, that is their greatest common divisor equal to 1? So these are all algorithms that you've already seen in secondary school. Now, even in elementary school, you did learn a number of algorithms. For example, very early on you learned how to add, subtract, and multiply two arbitrary sized numbers. First, you saw how to add two numbers using carries, and you saw how to subtract one number from another using borrows. Using addition, you were then able to multiply two numbers together by adding to a sequence of numbers together. You also then, later on in elementary school, saw long division, and then in secondary school you saw polynomial addition, polynomial subtraction, multiplication, and polynomial long division. Now, sometimes you may know an algorithm, that is, you know the steps involved in solving the problem, but you may not understand why that algorithm actually works. As an engineer, that's probably not a good idea, because understanding why the algorithm works also may provide insights as to some of the algorithm's limitations. But just to give you an example, here is an algorithm for calculating the square root of a number. So suppose we wanted to calculate the square root of this number here. We proceed as follows. Starting at the decimal point, we group the number in the digits in pairs. All right, starting with the first pair, but well, think of it as 0, 7. We find a number that we can place in both of those locations so that that number times itself is less than or equal to 7. Well, 2 times 2 is 4, 3 times 3 is 9, 9's greater than 7, so we're stuck with 2. All right, so now 2 times 2 is 4, like long division. We bring it down and we subtract it off of 7 and we're left with 3. Now, with long division, you bring down the next digit. With calculating the square root, we bring down the next 2 digits. The next step is to take the number above the surd, or that symbol, and we multiply it by 2. 2 times 2 is 4, and now we proceed. We now find the largest digit we can place here, such that that digit times 40, that digit, is less than or equal to 323. Well, if you work it out, 6 times 46 is less than or equal to that number, while 7 times 47 is greater than 323. All right, so 6 times 46, that's 6, carry the 3, 24, 27. All right, so 276, we subtract that from 323, that leaves 47. All right, so now we bring down the next pair of digits. Not a problem, and we double the number that's above the surd. Okay, twice 26 is 52. All right, and once again, we find the largest integer that we can place in both of those locations, such that that integer times 520 plus that integer is less than or equal to 4,761. Well, it happens that that number is 9. And it happens that 9 times 529 is that number exactly. Thus, the remainder is 0. And thus we have found that the square root of 72,361 is 269. If that remainder at the bottom was not 0, then we would have found a number that was less than the square root, and in fact, the largest integer less than the square root of the number. And you could actually proceed to find the square root of a real number as well, but you can look that up on your own. All right, I've described the algorithm, and most of you can probably implement this on your own, but most of you probably do not know why this algorithm works, and it does take a little bit of work to figure this out. If you're up to it, try to figure out why this algorithm actually works. However, this is more of an example of how you can know an algorithm but not actually understand why it works. All right, in the next few topics, we're going to find algorithms or design algorithms to solve the following problems on arrays. We will also implement these solutions or these algorithms in C++ as functions. First of all, we're going to start with searching an array, both arrays that are unsorted and sorted. We will then determine if an array is sorted, and finally we will look at two different algorithms that will sort an array. That is, take an array that is not sorted and rearrange the entries so that the result is sorted. The algorithms we will look at are selection sort and insertion sort. We're then going to look at an approach to solving problems. We're going to be looking at recursive algorithms. That is, an algorithm that takes a problem of a given size and breaks the problem into similar but simpler problems, uses the same algorithm to solve those one or more simpler problems, and then uses the solutions to these simpler problems to find a solution to the given problem. We're going to describe this and then apply this to a number of different examples where we will try to find problems that have recursive solutions. Now, an approach to designing an algorithm is called an algorithm design technique. And this is going to be the first algorithm design technique that you will see. And in your future courses on algorithms and data structures, you will see various other algorithm design techniques as well. So, following this topic, you now formally understand the idea of an algorithm. You understand that you've actually learned a number of algorithms both in elementary and secondary school. And you know that we will begin in the following few topics by looking at algorithms that solve problems on arrays, including searching and sorting. You also know that we will follow this by a description of recursive algorithms, and that we will look at how we can use this algorithm design technique to find algorithms that solve a number of various problems. Here are the references, the colophon, and a disclaimer. Cheers!